Laplace transformation of special signal waveforms. In the previous video, we have seen the basic types of special functions. Now we'll see the Laplace transform for those signals. The first one, unit step function, is given by u of t. Laplace transform of u of t is equals to integral 0 to infinity. Since it is a step function, unit 1 e power minus st dt. That is given by e power minus st 0 to infinity by s. Now for infinity this is 0, now for 0 this value is 1, so we are going to get 1 by s. Now the second function is shifted unit step function, Laplace transform of u of t minus t1, and the function we have seen at t1. This is our shifted unit step function. Then for this, integral t1 to infinity unit e power minus st dt. Now e power minus st by s between the limits t1 and infinity. If you substitute, then for infinity it is 0. For t1 we are going to get 1 by s of e power minus s t1. And we have one more shifted unit step function, that is u of a minus t, and graphically it can be represented as that. Then Laplace transform of u of a minus t is equals to integral minus a to infinity unity function e power minus st dt. Now e power minus st by s, and substitute the limits of t minus a and infinity. Then this is going to give us, for infinity it is 0, for minus a 1 by s e power minus s a minus so plus. Then for this function, if this t1 is replaced with a, then we are going to get 1 by s e power minus sa. For this function we are going to get e power plus sa. Third one, ramp function. Ramp function is given by r of t. Graphically it is represented with respect to time r of t from 0 to tan t, and this ramp function we are going to get by integrating unit step function from 0 to t. Laplace transform of r of t is equals to Laplace transform of integral 0 to t u of t dt. Integration of Laplace transformation, we have a formula. Laplace transform of integral f of t dt is given by f of s divided by s plus f naught divided by s. Let us neglect the initial condition, then we are going to get 1 by s of Laplace transform of u of t. Now Laplace transform of u of t, we know that it's again 1 by s, so you will be getting 1 by s square. If slope is m, then the Laplace transform is going to give us m by s square. When the ramp is going to occur at t equals to a, then r of t minus a, graphically represented like this, Laplace transform of r of t minus a equals to Laplace transform of integral 0 to t u of t minus a dt, that equals to 1 by s for integration. And for this function u of t minus a, we are going to get e power minus a s divided by s. Now the result will be e power minus as divided by s square. If slope is m, then Laplace transform of this function m multiplied by e power minus s by s square. Next, fourth one, impulse function. That impulse function delta of t with respect to t from 0 to infinity, and impulse function delta of t is given by d by dt of unit step function u of t. D by dt of f of t, Laplace transform of this function, we are going to get s f of s minus f0, and neglecting the initial conditions we are going to get s f of s is our formula. Now applying the same formula here, the Laplace transform of delta t is equals to the Laplace transform of d u of t divided by dt, that equals to, so first using this formula, s of Laplace transform of u of t. Now Laplace transform of u of t is nothing but 1 by s. So this value equals to 1 if the impulse function occurs at t1, which means 0 f of t, let this be t1, and this is a impulse function, the delta t minus t1. Then Laplace transform of delta t minus t1 is given by Laplace transform of d u of t minus t1 divided by dt. Then from the basic formula, s of Laplace transform of u of t minus t1. S of the unit step function, we are going to get e power minus t1s divided by s equals to e power minus t1 of s. This one, unit doublet function. And the doublet function is delta dash t minus t1 is nothing but differentiating the impulse function delta t minus t1. And the graphical representation, this is delta dash t minus t1. Laplace transform of delta dash t minus t1 is equals to Laplace transform of d delta t minus t1 divided by dt. That equals to, from the Laplace differentiation formula, s of Laplace transform of delta t minus t1. And we found that Laplace transform of delta t minus t1 is nothing but e power minus st1. Now let us summarize this. Unit step function at 0, graphical representation. For this, the Laplace transform is 1 by s, and unit step function at a, graphical representation is this. Laplace transform is 1 by s e power minus as. For the ramp function, graphical representation at 0 is this, and Laplace transform for this is 1 by s square. Graphical representation for the ramp function, which is going to occur at a, will be this, and 1 by s square e power minus as. Now impulse function, which is going to occur at 0, graphical representation, and the Laplace transform is 1. The impulse function occurs at a, then the Laplace transform will be e power minus as. Now doublet function at 0 at t. For this, Laplace transformation is yes if it occurs at 0. If this doublet function is going to occur at a, then s into e power minus as. Now unit parabolic function, which is going to occur at 0, then 1 by s cube. If this parabolic function is going to occur at t equals to a, then the Laplace transform will be e power minus s divided by s cube. This is regarding Laplace transformation of special signal waveforms. If this video is useful, please like, share and subscribe.